Yeah, so we want to look at a free response question in terms of what we would do with a related rates problem. So in this first one, they give you a curve and they ask you to find dy dx, or even tell you what dy dx is. We just need to prove that that's what it really is. So dy dx, so we're doing things with respect to x. So term by term, derivative of x squared is 2x. The derivative of 2x is 2. Derivative of y to the fourth will be 4y dy dx, because we're doing it with respect to x. And then derivative of 4y will be 4 dy dx. And it's going to equal 0 because the derivative of 5 is 0. We say next we have to isolate dy dx, so 4y dy dx will stay where it is. So will the 4, actually it should have been 4y cubed, I said it and didn't write it, 4 dy dx. And then the 2x and 2 are going to bring the other side. Minus 2x minus 2. Isolate dy dx, so we're going to factor it out, dy dx. This will be 4y cubed and 4. This will be negative 2x minus 2 still over here. Then we're going to divide to get dy dx by itself. Dy dx will equal 2x minus 2 over 4y cubed plus 4. Now, it's not the same as we have up here. It's pretty close though, so we're going to simplify it a little bit. I'll factor out a minus 2 up top, so I'll have x plus 1. Then I'll factor out a 4 on the bottom and have a y cubed plus 1. Well, I can then simplify the 2 and the 4. I'll get negative x plus 1 up top. Now I'll still have a 2 on the bottom, 2y cubed plus 1 on the bottom. And that is the same as what we had, or as what we wanted to show. Okay, so that's part A. We're going to use that same dy dx for the next couple ones as well. So part B, write an equation for the line tangent to the curve at the point negative 2, 1. So we're first going to look at, well, if we need an equation to a tangent line, we're going to need a slope. Well, the slope is the same as dy dx. So let's figure out what that is. At the point negative 2, 1, I'm just going to plug in negative 2 for x and 1 for y. So negative 2 plus 1. Then down here, y is 1 plus 1. So simplifying, we have the opposite of negative 1 up top, and we have 2 times 2 on the bottom, so I will have a slope of 1 over 4. Okay, now we need to use the idea of y equals mx plus b. Same thing, plug in my points. I have y value of 1, slope is 1/4. My x value is negative 2 plus b. So 1 equals negative 1/2 plus b, which means 3/2 is my value for b. So my equation in the end, y equals 1/4 x plus 3/2. That is my final equation of the tangent line. Part C, we now need to look at coordinates of 2 points where the line tangent is vertical. Well, we need to first know that when you have a tangent line vertical, that means that slope is undefined. That means that the slope is equal to something divided by 0. Well, remember, dy dx is what we're saying is our slope. So if it's equal to 1 over 0, that means my denominator needs to equal 0. That means my denominator. 2 times y cubed plus 1 must equal 0. Well, that means that either 2 equals 0 or y cubed plus 1 equals 0. Obviously, 2 cannot equal 0, so y cubed plus 1 equals 0. That means y cubed is equal to negative 1, which means y, when I take the cubed root, is negative 1. So, coordinates of the 2 points. So there should be 2 points where y is equal to negative 1. We have to look at not the derivative anymore. We need to look at the original curve and say, okay, when y equals negative 1, what are my 2 x points? So all I'm going to do for that is plug in negative 1 for x. For y, because we know y is negative 1. Plug it in. So negative 1 to the 4th plus 4 times negative 1 equals 5. Simplify it, so x squared plus 2x. This will become plus 1 minus 4 equals 5. X squared plus 2x. This becomes a negative 3. I'm going to bring it over to be 8. Bring everything back to the same side to simplify it. It should be minus 8 is equal to 0. Now, factors of 8 that subtract 2 to factor it. So factors of 8 that subtract 2 are going to be 4 and 2. And the bigger one gets positive, so plus 4 minus 2. So that means when I set x plus 4 equals 0, I'll get x is negative 4. And when I get x minus 2 equals 0, x is positive 2. So my final answer should be the coordinates, which are the ordered pairs negative 4 comma negative 1 and 2 comma negative 1. That's my final answer. That's my two coordinates based on my x and y values. Okay, the last part of the problem, possible for the curve to have a horizontal tangent where it intersects the x-axis. Alright, there's two parts to this. First, I'm going to look at horizontal tangent. And when it's a horizontal tangent, that means that the slope must equal 0. So that means dy dx must equal 0. So that means if this whole thing equals 0, that means the numerator needs to equal 0. So I'm going to say the opposite of x plus 1 equals 0, that means x will equal negative 1. So whenever x equals negative 1, that's when you have a horizontal tangent. Okay? Now, we also want to look at intersecting the x-axis. That's the same thing as saying that y is equal to 0. And in this case, we need to look at my original equation, the curve itself. So remember, this deals with the curve. This part deals with my slope. dy dx deals with slope. So when I'm looking for intersecting the x-axis, that again means that y equals 0 in my original equation. That means that these values will just go to 0, and I'm left with x squared plus 2x equals 5. X squared plus 2x minus 5 is equal to 0. Okay? So, well, if it's the same thing and having a horizontal tangent when it intersects the x-axis, that would mean that if I plugged in negative 1, this would be a true equation. And if I did that, it would be negative 1 squared plus 2 times negative 1 minus 5. Does it equal 0? That's 1 minus 2 minus 5. Does it equal 0? No, it does not. So the final answer is no, it's not possible, and your reasoning is just your work, that it can only happen at one point, and it doesn't cross the x-axis. So that's how you do that one. Let's look at another related rate. This is more of a word problem one. We're looking at the square. So when we're doing this, we have area equals side squared. So we want to say here, again, same thing. If a equals s squared, we're going to be taking a derivative. So dA dt will be equal to 2s ds dt. Now we need to plug in what we know. The square has an area of 4 inches. So area equals 4 inches squared. That would mean that the side length would be the square root of that, so 2 inches. We also know that side length is increasing. Side length is ds dt. ds dt is 0.5, 0.5 there. At what rate is the area changing? dA dt, the area rate changing. That's what we don't know, that's what we need to find. So to do that, just plug in 2 times the side length is 2 times ds dt is 0.5, which means that I get 2 for this. Now, we want for units, the unit, we look just based off this. Area up top, which is in inches squared, and time, which we've been saying is seconds. So my unit is 2 inches squared per second. Number 2, or part B I should say, if the area is increasing at a constant rate, is side length increasing more rapidly at 5 inches or 6 inches? So we're going to need to do 2 different parts of this. So again, the same sort of formula we had, dA dt is equal to 2s ds dt. That's what we had from before. And we want to say, okay, that dA dt is increasing at a constant rate. So that's why we look at, and the constant rate is equal to, make it equal to 10 square inches per second, inches squared per second. Is the side length increasing more rapidly when the side is at 5 inches, or at, it should say actually, 6 inches here? So, we're going to do 2 different problems here. Set it up 2 ways. One with it 5 inches, one with it 6 inches. dA dt is equal to 10. 2 times, we're going to make this side length at 5 inches, ds dt. So when we do this, we're going to have 10 over here, 10 divided by 10, so ds dt is going to equal 1 when the side length is equal to 5. When side length is equal to 6, we'll have the same thing. It's still 10, it's equal to 2 times 6 ds dt. So when I do that division, 10 over 10 over 12, which is the same as 5 over 6, is equal to ds dt. So, which is bigger? It's bigger. ds dt is bigger when s equals 5. So, s equals 5, it's, so I should say ds dt is larger. ds dt is larger when s equals 5. And you're, again, justifying your answer is just showing your work. So it's increasing more rapidly when the side length is at 5 inches. Okay, and then problem C, the area of the square increasing at a constant rate. Again, so we don't know what it is, but we need to figure it out. At 2 seconds, so when we have at 2 seconds, or I should say, at time equals 2, we have the area is equal to 12 square inches. 12 square inches. At time equals 5, we have the area is equal to 36 square inches. They want to know what is the rate the side length is changing. Well, to do that, we're just looking at slope with that one. So I'm going to say that I'm going to look at time equals 5 what the area is. So essentially, this is saying dA, dt, it's kind of like a slope. So from 36 to 12, that's what the area is. Change in area, change in time. That's all dA really means. It's kind of like a delta A and a delta T. So we have 26, 24 up top, and 3 on the bottom. That means I have 8 inches squared per second. That's what dA dt is. Well, dA dt is one thing, but we need to know what ds dt is. Well, if the area is increasing at 8 square inches per second, that would mean that the ds dt would have to be, well, if the area is 8 square inches per second, we would have to have the square root of 8 inches per second to be able to have the side length as this. So there you go. Because the side of the square is equal to one of the other. Or side squared gives you that area. Hopefully this helps. Hopefully it doesn't confuse you more, but hopefully this is something you can come back to later on and be able to solve problems like this without my assistance. Good work.